They're small enough to hold in your hand, yet powerful enough to lift entire ships, anchor oil rigs, and haul millions of tons of steel. We're talking about the world's toughest steel chains, forged in roaring furnaces hotter than lava. Today, we'll step inside a mega chain factory where molten metal, giant hammers, and precise craftsmanship come together to create links stronger than any weak point. But before we dive in, make sure to subscribe for more incredible looks inside the world's biggest and boldest industries. The art of forging chains dates back to the early 1800s, when blacksmiths hand-hammered iron links for ships and bridges. But the real revolution came during the Industrial Age, when steam power and new steel alloys transformed chainmaking into a precise science. Today, modern megafactories continue that tradition with robotic precision, AI-controlled furnaces, and metallurgical expertise refined over centuries. Future innovations include smart chains with embedded sensors that track stress, wear, and load in real time, helping industries predict failures before they happen. From simple hand tools to global infrastructure, the humble chain has evolved into one of the most critical links of modern civilization. From massive cargo ships crossing oceans to mining trucks carrying hundreds of tons, steel chains are everywhere. Unseen, but essential. Each link bears tens of thousands of pounds of force, working silently to keep the modern world moving. In America's industrial heartland, these mega factories produce the heaviest duty chains on the planet. Some links weighing more than 150 kilograms, 330 pounds each. They're built for extreme conditions. Deep-sea moorings, offshore platforms, heavy cranes, and military applications. But unlike ordinary steel chains, these are made with precision forging, alloyed metals, and heat treatments that make them almost unbreakable. The process combines ancient craftsmanship, the art of forging, with advanced metallurgy and robotics. Every step, from the first spark of molten steel to the final polish, is carefully designed to produce one thing: strength without compromise. Let's step inside the factory where steel meets fire, and where every link tells a story of human engineering at its peak. The journey begins with massive steel billets, each weighing several tons. These billets are cut into smaller sections, the raw chunks that will become individual chain links. They're then fed into industrial furnaces burning at over 1200 degrees Celsius, 2200 degrees Fahrenheit, hot enough to make the steel glow bright orange. At this temperature, the metal becomes soft and pliable, ready to be shaped. Using automated robotic arms, each heated section is transferred to forging presses or hydraulic hammers that deliver thousands of tons of force. In just seconds, the red-hot bar is bent, pressed, and hammered into the shape of a link, precise and consistent. While the process looks violent, it's incredibly controlled. Each hammer strike is timed by computer sensors to ensure the correct density and alignment of the steel grain structure, the microscopic pattern that gives metal its strength. Once forged, the open ends of each link are welded shut using flash welding, a process that fuses steel under both heat and pressure, ensuring a seamless, solid joint. This is the heart of chainmaking, a dance between fire and force, where machines mimic the skill of blacksmiths, but on a superhuman scale. Freshly forged links are strong, but still not tough enough for the brutal demands of the real world. That's where heat treatment comes in. The entire chain is moved into giant furnace tunnels, some stretching over 100 meters long. Inside, controlled cycles of heating and cooling alter the metal's molecular structure. First, the chain is austenitized, heated until the steel's carbon atoms dissolve and realign. Then, it's plunged into oil or water baths in a process called quenching, locking in hardness. Finally, it's tempered at a lower temperature to relieve stress and restore flexibility. This delicate balance gives the steel its dual nature: hard enough to resist wear, yet tough enough to absorb shock. After heat treatment, the chain is shot blasted with steel pellets to remove scale and smooth the surface. Then, it undergoes non-destructive testing, NDT, using magnetic fields and ultrasonic waves to detect even microscopic cracks. One defective link could mean disaster in the field. So every millimeter is examined. Only flawless chains move forward to final assembly. As one engineer says, the chain is only as strong as its weakest link. And here, we make sure there are none. Once the chain passes inspection, it's time for the most dramatic test of all, the proof test. The entire chain is laid out on enormous steel beds and pulled with hydraulic tensioners, applying hundreds of tons of force, simulating real-world conditions. If a link shows even the slightest deformation, it's scrapped immediately. Those that pass are measured, stamped, and certified with unique serial numbers for full traceability, each one recorded in the factory's digital system. Next comes finishing and coating. Chains are galvanized, painted, or powder-coated depending on their application. For offshore use, special anti-corrosion layers protect against saltwater for decades. For industrial cranes, coatings reduce friction and wear. Finally, the finished chains, some stretching hundreds of meters long, are coiled, loaded onto massive trucks, and shipped to ports, mines, and factories worldwide. What started as a glowing bar of steel is now a vital component of human progress, ready to lift, anchor, and hold the heaviest burdens on Earth. If you loved exploring the Mega Chain Factory, don't forget to subscribe, like, and share, because more amazing stories of human engineering are just one click away. Today, we're taking you inside America's supergiant gold recycling plants, where mountains of e-waste are transformed into pure, gleaming gold. For most people, electronic waste or e-waste is just junk. But hidden inside these discarded gadgets is a fortune, tiny traces of gold. In fact, a single ton of old circuit boards contains more gold than a ton of ore mined from the earth. Before we dive into this mind-blowing process, don't forget to like, subscribe, and hit the notification bell so you never miss our deep dives into the hidden worlds of global industries. For decades, people threw away old radios, televisions, and the first computers without a second thought. Back in the 1960s and 70s, few realized that inside these machines, on their green printed circuit boards, lay traces of one of the world's most valuable metals, gold. At the time, these boards were simply considered electronic trash. It wasn't until the boom of personal computers and mobile phones in the 1980s and 90s that the hidden value began to attract attention. Millions of circuit boards were being discarded every year, and scientists started experimenting with ways to recover the precious gold hidden in their thin layers and connectors. Early methods were crude and dangerous, often involving toxic chemicals like cyanide or mercury. Still, the realization had been made: electronic waste could be richer than natural ore. By the 2000s, with the explosion of smartphones and the internet, mountains of e-waste were piling up worldwide. Governments in the US and Europe introduced new regulations pushing companies to recycle responsibly. High-tech plants were developed using shredding, smelting, and electrolysis to safely recover gold. For the first time, recycling gold from PCBs became an industrial process, not just an experimental idea. The journey begins in massive collection centers across the US. Old computers, servers, cell phones, televisions, and other devices pour in by the truckload. Workers and machines sort through this mountain of e-waste, separating plastics, steel casings, and valuable electronic components. The focus is on printed circuit boards, the green boards dotted with chips, capacitors, and connectors. These PCBs are the treasure maps of modern electronics, hiding tiny but valuable amounts of gold along their pathways and pins. In a supergiant recycling facility, conveyors carry thousands of pounds of boards every hour, feeding them into shredders that grind the boards into small fragments, making it easier to extract the precious metals. Once shredded, the e-waste fragments undergo a series of mechanical separations. Powerful magnets pull out steel. Eddy current separators remove aluminum and copper. What remains is a concentrate of plastics and precious metal-rich material. This material is then ground into fine powder, almost like dust. Why? Because the finer the material, the easier it is for chemical processes to access the metals trapped inside. At this stage, the powder still looks like waste, but within it are flecks of gold, silver, palladium, and other valuable metals waiting to be reclaimed. Now comes the most fascinating and delicate part: extracting pure gold using chemistry. Traditionally, gold is separated using harsh chemicals like cyanide or mercury, but modern American recycling plants employ safer, more sustainable techniques. One of the most common methods is aqua regia, a mixture of hydrochloric acid and nitric acid that dissolves gold into solution. Here's how it works. 1. The ground e-waste is mixed into giant chemical tanks. 2. As the solution works, base metals like copper dissolve first, leaving behind the precious metals. 3. Gold, being more resistant, requires special conditions to dissolve. Once it does, it exists in liquid form as chloroauric acid. 4. To recover it, engineers add reducing agents that cause pure gold to precipitate back out of the solution as fine particles. These tiny particles are then filtered, washed, and dried, leaving behind a brownish gold powder known as gold precipitate. The precipitate is not yet the shiny gold you imagine. It must be refined. The powder is collected and melted in high-temperature furnaces, reaching over 1,100 degrees Celsius. As the powder liquefies, impurities rise to the surface and are skimmed away. What remains is 99.99% pure molten gold. Workers carefully pour this glowing liquid into molds, where it cools and solidifies into gold bars, coins, or granules. Each bar is stamped with its purity and weight, a mark of value recognized worldwide. It's astonishing to realize that this bar, worth tens of thousands of dollars, came not from a mine deep in the earth, but from old smartphones and computers that people once tossed away. Gold recycling is more than just profitable, it's vital for the planet. Extracting 1 ounce of gold through mining can produce over 20 tons of toxic waste rock. By contrast, recycling requires far less energy and reduces greenhouse gas emissions significantly. However, the process isn't without challenges. Handling e-waste involves toxic substances like lead, mercury, and brominated flame retardants, which must be carefully managed to avoid harming workers or the environment. That's why modern American facilities use advanced filtration systems, closed-loop chemical processes, and strict environmental standards to ensure safety and sustainability. Globally, only about 20% of e-waste is properly recycled, meaning that mountains of valuable materials are still being dumped or burned, releasing toxins into the environment. The US, however, is home to some of the largest and most advanced e-waste recycling plants in the world. These facilities not only recover gold, but also silver, platinum, copper, and rare earth metals, essential for building new electronics, renewable energy systems, and even electric vehicles. As demand for technology grows, the importance of this industry will only increase. In fact, experts predict that by 2030, the value of urban mining, recovering metals from waste, could surpass traditional mining in certain sectors. If you found this journey fascinating, make sure to like the video, subscribe to the channel, and hit the bell so you never miss another deep dive into the world's most mind-blowing industries. Thanks for watching, and remember, the next time you hold a smartphone in your hand, you're holding a little piece of gold. Millions of American homes stay warm and cozy thanks to a material that few people ever think about: rockwool insulation. Rockwool, also called stone wool, is one of the most effective and sustainable insulation materials in the world. It's fire-resistant, water-repellent, sound-absorbing, and incredibly durable. And the best part? It's made almost entirely from natural stone, basalt, combined with recycled slag from steel mills. Today, we'll take you inside the supergiant rockwool factory, where raw basalt is transformed into high-tech insulation, step by step. From quarries to furnaces, spinning machines to packaging lines, and even into homes across America, you'll see how this incredible product is born. But before we dive in, don't forget to like, subscribe, and hit the bell icon so you never miss another behind-the-scenes look at how the world's most essential materials are made. It all starts with basalt rock. Basalt is a dark, dense volcanic stone formed millions of years ago when lava cooled rapidly at the Earth's surface. It's abundant, incredibly strong, and naturally rich in minerals like silica, alumina, and iron oxide. In quarries across the US and around the world, enormous machines dig, drill, and blast basalt from the earth. Giant excavators scoop up boulders weighing several tons, which are then loaded into heavy-duty dump trucks. These trucks thunder down the quarry roads, carrying their black rock cargo to be crushed and sized. Once at the processing plant, the basalt is broken down into smaller chunks, about the size of a fist. Why? Because these chunks are easier to feed into the furnaces that will melt them. At this stage, it's almost impossible to imagine that these dark, jagged rocks will soon be transformed into something as light and woolly as insulation. But once inside the factory, fire and air will completely reshape their identity. Inside the supergiant rockwool factory, the first jaw-dropping step is the melting process. Basalt rocks and slag are fed into gigantic cupola furnaces, massive, cylindrical ovens capable of reaching 500 degrees Celsius, 2,732 degrees Fahrenheit. Here, the rocks don't just heat up, they turn into a glowing, liquid lava. Flames roar, fans blast oxygen into the furnace, and the roar of the machinery makes it feel more like the inside of a volcano than a factory. This is no coincidence. Engineers are literally recreating volcanic conditions to melt rock back into magma. The molten lava collects at the bottom of the furnace, glowing orange and yellow. It's tapped continuously through a spout and flows like honey into the next stage of production. Workers in protective suits monitor every detail: temperature, viscosity, chemical balance, because even the slightest variation can change the quality of the insulation. Watching solid stone transform into liquid fire is breathtaking.